Alessandro. So, hello everyone, and welcome to today's lecture. Today, I'm going to talk about the inductive biases in data augmentation and its interplay with adversarial robustness in deep neural networks. Just a question, can everyone hear me well?
Yes.
Yes.
Okay, very good. All right, so some notes before I start the talk. So there will be some slides where you can ask questions. It would be nice if you could write your questions and then ask your questions in those slides with this logo or icon. Another thing is that the recording will be made available by Alessandro. You can ask him how this is done in case you wanted to have access to the video. And the slides will be also made available for those who are interested. All right, so I start with an overview. So there will be a somewhat brief introduction to the concepts that we need for this talk and the inductive biases in deep learning and adversarial robustness and the data augmentation. And next, I will be detailing an analysis framework that can be used to actually investigate the relationship between these concepts. And in the end, there will be some results shown using this analysis framework and some experimentations. All right, so I first start with the inductive bias. So what I mean by inductive bias in this talk is a series of assumptions that we have for a specific system when we want to make some predictions about that system. For example, imagine there is a tree and there is an apple on the tree, and we want to predict what happens to the apple next. And if we know that there is some gravity, it's most likely that we predict that the apple is going to fall on the ground and not, for example, jump up. And this is an inductive bias that allows us to make this prediction about this system. Another example is that, for example, we want to build the relationship or learn the relationship between two variables via some function, and we are looking for this function. And while this relationship could be of any kind, if we have some specific assumption, for example, if we know that this relationship is going to be linear, then we look for specific classes of functions, or, for example, linear functions that allows us to easier find what we are looking for. So these were some simple examples of what I mean with inductive bias when I'm talking about inductive bias. Another concept that you may have probably heard of by now is data augmentation. And what I mean by data augmentation is the techniques that we use, especially in deep learning, to extend the training data that we have to train our models. For example, imagine we have some training examples like these, and we want to separate these two classes from each other, the orange from the blue. And this is the training data that is given to us. And if we train a model to separate these, we don't actually have the full distribution. We just have the training part of the distribution. And some parts are missing. We don't have the full data from these two classes. And if you only train a model on the training set, we get something like this, a decision boundary that separates these two classes, which actually is not perfect and makes some mistakes, which is not very ideal. So the decision boundary that this model gives us is not that ideal. What we are looking for, given the augmented data augmentation, is to try to come up with some examples that can fill these missing parts as much as possible to give us a better decision boundary for this task that I gave in this example. There are many different classes of data augmentation, one of which is known as classic augmentation, or augmentation that is based on domain expert opinions or experiences. For example, if we are working with natural images and we want to use data augmentation, and if our task is, for example, image classification, and one of the classes, for example, is a dog, an expert knows that horizontal flipping of the image of a dog is still an image of a dog, so it doesn't change the meaning that we are interested in the task at hand and in the data set that we are working with. So this is a good augmentation to be used. Whereas if we are using classification on numbers, for example, on a data set such as MNIST, an expert could tell you that if you rotate this image, a 6 could turn into a 9. So rotating by 100 degrees might not be a good data augmentation technique. All right. So another class of data augmentation are the methods that combine existing training examples and come up with new examples. And this way they extend the training data. And one of the famous examples of this class of data augmentation is mix-up, which I will explain later on in more details. And the last class of data augmentations that we will discuss in this talk are the class of generative models. And the goal is actually to learn a proxy distribution from the training data and then use this proxy that they learn to come up with new examples and generate new samples from this proxy distribution that they learned. And I use the term proxy because they cannot really learn the real distribution of the data, so they approximate it somehow. And the last term that we are dealing with in today's talk are adversarial examples, which is the main discussion on adversarial robustness. And what the adversarial examples are is actually a very interesting topic. It turns out that in specifically deep neural networks, if we have a model that can predict with a very high confidence on a, for example, sample of an image of a panda, there are very small perturbations that we can carefully create or find in the data space that can be added to the original image. And while the difference that they make to the human eyes are very small, they make actually the prediction of deep neural networks change drastically and with a very high confidence predict to any class that actually is wrong. So these are known as adversarial examples, and this is a big topic nowadays in machine learning and deep learning. And it has been shown that these are not exceptions that are in the data space. Actually, these can be constructed to be placed in the physical world. For example, we can come up with some stickers and place it in some signs, and this can fool the models. And it also has been shown that these examples are very universal. They are not too specific to a class of models or specific databases. They can transfer from one class to another, from one dataset to another. So overall, it's a very big problem, especially when dealing with deep neural networks. So in short, with a simple definition, I want to explain how we get an adversarial example. Imagine we have a neural network H parameterized by theta working on data space X. And we have a loss function that we use for training the parameters of our network by minimizing that loss. To find an adversarial example, given a fully trained model, we can just maximize the loss by changing the input x hat and find an input x hat that actually increases or maximizes the loss given our neural network. This is actually a simple definition for adversarial example, which we can actually rephrase it a little bit. And instead of looking for an input, we can look for a small perturbation like delta that can be constrained somehow to be very small, for example, within a specific norm with a specific radius, and then we can look for this delta. And this delta can be constrained with LP norms, for example, L infinity or L2. And if you look at this example, this is, for example, a loss landscape of a model, and this is sample X that we show in this formula. And what we are doing in here is we take small steps within this epsilon ball, for example, this L2 ball, to move from a low loss region to a high loss region that is likely to flip the prediction of our model. All right, so if there are any questions so far, feel free to ask. Otherwise, I will continue. Okay, then I will continue.
I have like a very small question.
Okay, sure, go ahead.
Again, like which one would be the better norm to use, or like is that a best one?
So it's not actually about being better when you are creating, for example, defenses or certified robust models. You usually target a specific norm. For example, if you provide a model that is robust towards a specific LP norm, for example, L2 or L infinity, then this shows how robust your model under that specific LP norm is. So it's mostly to show that, I mean, it depends on the use case. If you care about the maximum amount of a specific dimension in your data, then probably you can use L infinity, or if you are just looking for overall difference in hot data space, probably you will go with something like L2. But this is just an example. There are also measures beyond LP norms. There are other measures that is not really, I think it needs its own session to talk about. So it will be a long discussion if we want to talk about that.
Okay, thank you.
I can a question as well. Did you say what's the X hat in the second column?
So the X hat is what we are trying to change in order to maximize the loss. This is the overall definition. We have a loss and we have a neural network with some parameters, theta, and we use some algorithms such as gradient descent, and we update X hat such that it gives us a loss that is very high. But in reality, what we do in adversarial attacks, because we don't want to come up with something that looks like noise, so we don't optimize the whole input, we optimize or we change a small perturbation that is limited or constrained with some norm that can be added to a specific image. For example, in this panda, the image of a panda, this is the delta, and delta plus this panda is X hat. So this on the right-hand side is what we feed to the network, and this small noise is what we find given the model. So this is the small perturbation that we add to an image that already exists, and these two together will create the adversarial example. That to us looks no different than the original image, but to a neural network actually looks very different. All right. Okay, so in today's talk, we look into 3 popular classes of data augmentation and see what they do to models and what actually happens to the models that use these data augmentations in terms of adversarial robustness. One class is traditional or classical data augmentation, and as I mentioned before, it's based on incorporating some domain expert knowledge into the model. For example, for images, horizontal flattening is useful. The second class are the models that combine the existing training data and come up with new pairs of data and labels. And in this case, we use mix-up, which is a very well-known data augmentation technique. And for the last class, for generative models, we use conditional GANs, which are trying to generate new samples given a specific label. So we ask a model to give a sample for a specific label, and then we actually use that. All right. So we actually talk about an analysis framework for systematically evaluating these data augmentations with respect to the risk under attack and the classification risk or the classification error. Given this framework, we analyze these three classes of popular data augmentation, namely classic, mix-up, and GAN augmentation. And in addition, we also provide a formal definition for data augmentation, which is based on some definition in probability theory and random functions, which allows us to, first of all, define complex data augmentations using the composition of simpler functions that can allow us to define a data augmentation such as GAN under a theoretical definition that we provide. And we also provide a measure known as prediction change stress that we use for evaluating models, and we show that this property is related to adversarial vulnerability of models, and we also show how it can be used to evaluate models. And in the end, we use influence functions to examine how much influence the models that use a specific augmentation data receive from the real and from the augmented data. I will detail the definition of exactly what I mean by influence function and by prediction change stress. All right, so here is our formal definition. We define a data augmentation, a random function such as A, which maps a sample S with a measure P of X on data space X, and a labeling function such as L to some vector A of S. And these random functions A of S are independent random vectors with some measure P of X times Xi times Yi on the joint space of data and labels, and a marginal measure P of Xi that is dominating P of X. I will explain what it means. It's just based on the definitions from probability theory that has to be constructed this way. And what I mean is that for an augmented sample S hat, we can actually sample our augmentation and then observe an augmented version. So by observing actually A of S, we observe an augmented data, and we can infinitely sample and observe it every time a new augmented example from augmented sample from our training set. And domination, or when we have this assumption of P of Xi dominating P of X, is just to ensure that data augmentation takes the original sample into the account. For example, if you have a non-zero measure for the original data, we make sure that our augmented data is also non-zero for any measurable D. So this measure is very general because then you can take it into the account if we are interested in preserving the label of the data or anything else. And this definition allows us to take all of this into the account. And one lemma that is the direct consequence of our definition is that if we have two augmentations, such as A of S and B of S, then the composition of these two are also a valid augmentation. And given the definition of and this lemma, we can now define classic data augmentation, conditional generative models, and sampling from vicinity distributions such as mix-up as valid augmentations. We provide a couple of examples in a paper that I will provide by the end of this talk, a link to the paper, that how these three are constructed given our definition. But you can think of it as if you can define a simple augmentation such as adding some noise given our definition and then flipping by another data augmentation definition, then combining adding noise and rotating or flipping is also a new data augmentation that is valid. And this way you can build more complex data augmentations such as these three. All right, any questions so far for this part? All right, then I move on. All right, so we are talking about now the adversarial robustness in data augmentation. And what we are focusing in this part is to analyze from three different aspects. One is the performance analysis, where we want to look at the specific data augmentation, and we want to see what happens if we train a model with this data augmentation with respect to classification performance and adversarial robustness. So this is what we call performance analysis. Another part that we will cover is stress analysis, and this part actually is focused on analyzing how the prediction of a model that is trained with a specific augmentation is changed when you are showing it some adversarial examples or some normal examples. And we want to show that how the prediction change actually is affected by the augmentation. So this is what we discuss under the stress analysis. And the last part is influence analysis, where we look at how much a model relies on augmented data when it's predicting on, for example, real samples or adversarial samples, and how much it is relying on augmented data. And this is discussed under influence analysis. Each of these will be explained in detail again. All right, for the performance analysis, we analyze the model with respect to usefulness and adversarial robustness. For that, we apply a specific data augmentation, for example, classic data augmentation with a specific probability that is changing from 0 to 1. And for example, we train a model with classic data augmentation with probability of 0.1. And then we train this model to the end. And then we take this fully trained model that was trained with 0.1 probability of classic augmentation, and then we evaluate it. And for this experiment, we use a Resonant 15 neural network and the training data of cycle 10. And then we report the normal test error, which represents the usefulness of that specific augmentation. And also, we report the risk under attack, which are the classification error when a specific adversarial attack is conducted to that model. And for the risk under attack, we conduct 4 different projected gradient descent attacks, where 2 different epsilons are used and 2 different number of iterations. Epsilon is actually the radius of the norm that we are constructing our attacks on, and the iteration is how many times we are actually updating this perturbation to find the best perturbation possible to break the prediction, to break the model. So we chose these 4 different conditions because we wanted to also have attacks that are not very strong and attacks that are very strong, and then see how different models trained with different augmentations behave. So for the stress analysis, I will start with an example. assume we have two different models that are trying to separate these two classes from each other, circle from the rectangle, and they come up with two different boundaries. Model 1 comes up with boundary 1, which is a very smooth decision boundary, and model 2 comes up with this non-smooth boundary that also separates these two classes from each other, but in a different way. So which one is better? Which one is more useful for being a adversarial robust model? For that, we can look at a small neighborhood around our sample and see whether or not this neighborhood actually crosses the boundary. We can see that if we have a smooth boundary, it's less likely that the decision of the model is flipped, while if we have a non-smooth boundary, then it's very likely that the decision of the model is flipped quite easily. And that's what adversarial examples do. If you look into this neighborhood, we can see that it's much easier to find an adversarial example with this model around with this decision boundary compared to this one. So now we want to come up with a measure that can tell us if a model has a boundary that looks like this or the other. And this is the definition that we are using. And we call it stress analysis on a sample S. We first place an epsilon ball around a training example X or any example X with a radius of epsilon. And we introduce the prediction change stress as the average probability of the samples that are sampled uniformly from the surface of this ball. And then we measure the probability of the prediction of the samples from the surface of this sphere being different than from the prediction of the original example itself. So given an input X and its predicted label given our model f of X, the stress relates to the probability that a random uniformly selected sample from the epsilon sphere around X will be assigned a different label. And if this value is higher, it shows that the prediction of the model is more likely to change, so it has a higher stress, and if it's lower, it shows that the prediction of the model is less likely to change. Any question regarding the definition of stress?
Yes. Actually, what's roughly the complexity of stress analysis with this kind of technique?
So it depends on the sampling, because it's a sampling-based approach. For each sample that we use, for example, if we want to measure the stress around the training set, for each training example, we sample several thousand examples, and then we measure this probability for each example, and then we can report the average over all of this stress. But since this can be done very quickly using GPUs, it's not a very time-consuming measure. For example, compared to other approaches, which is conducting an adversarial attack, it's much less computationally expensive.
Okay, I have also a question about the previous section.
Mm-hmm.
Actually, can you use data augmentation on regression?
I think so. I mean, you can use it in any model. It's not really limited to a specific class or task.
Okay, I was have to think better about it.
Okay.
Thank you.
Sure. No worries. Okay.
I also have a question, if I may.
Sure. Navid, go
So
ahead.
this stress analysis here is do we want to create adversarial do we want to measure the robustness of the model, or do we want to create adversarial data points? What does it do exactly?
So the goal is to see if our model looks something like boundary 1 or something like boundary 2. And we show that a model that has a boundary such as boundary 2 has a high stress, which means its predictions can be flipped very easily. So if it's a model, as we will show later, is a model that is less robust towards adversarial attacks. But we don't do this with respect to a specific distribution. We do this without having any assumption about the distribution of adversarial examples. For example, we are not looking into an adversarial distribution, we are uniformly sampling because we are not looking into a specific attack with a specific norm. For example, we are not looking into the attacks of TGD with L2 norms. What we are assuming here is that we sample uniformly, which is more general. So our measure can tell you for any specific distribution that is close enough to our data distribution, how likely is it that the prediction of our model changes.
So it basically tells us something about smoothness of the decision boundary, but not necessarily about the robustness against adversarial attacks.
Precisely. And we have in the literature adversarial examples that the definition of smoothness is actually strongly related to adversarial robustness. Mm-hmm. So this connection is already made in the literature, and we are providing a measure that actually connects the smoothness to the adversarial robustness without actually conducting a specific attack.
So if you have the epsilon larger, then it basically goes, it just predicts another.
Right. So if
and it might be correct to just do another thing. It's not necessarily wrong or right. It just tells us how so smooth is the decision boundary. Okay, got it. I think I got it.
Yeah. So it was a very good point. However, I want to mention that the definition of epsilon ball is open. We provide several examples of how you define this epsilon ball. For example, we provide in our paper for LP norms, how we define LP norms, but the norm is open to be chosen. You can choose an adversarial epsilon ball. So you can choose to not sample uniformly from an L2 sphere. You can choose to sample from an adversarial distribution. So this is also a very general definition that can, by itself, it's very general, but can cover also the specific adversarial attacks. You just have to change the definition of epsilon ball. All right, very good question, Navid, by the way. All right, so we move on to the influence analysis. So we use a specific definition of influence function proposed by Quan Liang to analyze the importance of non-augmented and augmented training data in relation to the adversarial vulnerability of our models. I give a short recap for those of you who are not familiar with influence functions. So what influence functions, as presented in Quan Liang, do is that they come up with some importance value for each training point that shows how much each of the training data contributed to the prediction of a specific test example. And they do this by estimating the change in the loss on that test example that actually can be done if you remove a specific training point and then retrain the model. So I will give an example to make it more clear. Assume we have a model that is separating these two classes. There is a decision boundary and there is a loss landscape of that model. And this is the training data that we have to train this model. And we are interested to see for example, for this given unseen test example, what is the influence of this specific training example for this model that we already trained? So what we do is, first of all, to see, okay, what is the loss of our unseen test example? For example, in this case, is 0.2. And then we remove this training data that we were interested in. We retrain the model without that specific training example, and we remeasure the loss for that specific test example. And in this example, we see that the loss is now 0.3, so the loss has increased. And we measure the differences of the loss with and without that training data. And we see that after we remove this training data, the loss has increased. So the existence of that training example was actually positive in predicting on this unseen test. So it was actually useful. So we say that the influence was positive on 0.1. But since it's very computationally expensive to remove every training data and retrain a model, they come up with a closed form solution that can estimate this change in loss, which is actually using the Hessian matrix of the parameters of the network and the gradient of the loss for the test and for the training example. So they come up with this closed form and they show how it correlates with the influence of training examples. And we use this as a tool to analyze the influence of the augmented and non-augmented training data when models are predicting on normal tests and adversarial examples. All right. And we show then the distribution of influence values for all these cases to get a bigger picture. Okay, any questions about influence functions? Very well. All right, so I will now show, so now we know these three aspects that we are using in our analysis. We have performance analysis, we have stress analysis, and we have influence analysis, and this is our experimental setup. We use ResNet 50, which is a convolutional neural network, and we train it using stochastic gradient descent on CIFAR-10. For those of you who don't know the CIFAR-10 data set, it's an image data set, has 10 classes, and has tiny 32 by 32 pixel images. So we train our model just to see how far our model can get, and it achieves around 95% accuracy, which is acceptable for this model and this data set. And for each of our augmentations, we apply an augmentation with a probability from 0 to 1 on this order that you see in here. And we train the models, each of these models to the end, and we repeat each experiment 3 times. And then for each of these, we report mean and standard deviation for each of these experiments. And for our generative models, we use 2 conditional GANs, which are conditioned on the labels. And we also evaluate them with FID to make sure that they achieve reasonable image generation performance. For example, in here, we see some examples that are generated. Each row has a fixed label as a conditioning, as a condition, and then we sample several times to get several examples just to visualize how each model looks like. And here are the results. In the middle, this is the classification error for different augmentations, and the x-axis shows the probability of augmentation, and the y-axis shows the test error. And what we can see in here is that when applying classic augmentation, we see the error actually significantly decreases by the augmentation, which shows that the classic augmentation is actually very effective in reducing the classification error. We also observed a marginal improvement over the classification error for mix-up and a very small or even non-existing decrease in classification error when only using generative models such as these 2 GANs. And the rest of the plots, these 4 plots are the risk under attack. which show the classification error when a specific adversarial attack was conducted. Looking at the first one, we can see an interesting trend. As we can see here, when we increase the augmentation, the risk under attack for classic augmentation as well as for GAN augmentations more or less stays the same, maybe a marginal even improvement, while for mix-up, this risk under attack actually significantly rises, which shows that actually the mix-up augmentation is hurting the adversarial robustness of the models. And while looking at the other attacks, we observe a similar behavior, that mix-up actually increases the risk under attack for all the attacks. And for the last one, it's a very strong attack. We see that all the models are broken because these are not actually robust models, so we expect this to happen. Okay, any question here, actually, because it's a lot of results.
May I ask one?
Sure, go ahead.
So what was the probability? Sorry, can you remind me? What was the probability of augmentation?
Right, so for example, in the plot that says 0.1, or here 0.1, it means that with the probability of, with 10% probability or probability of 0.1 actually, we augment our training data. And then we train a model to the end. And then we evaluate, for example, this blue column in here shows that a model that was trained with 0.1 probability of classic augmentation achieved the error classification error of 10. And there is
so
a
what is that? Is
standard.
Is it 10% of the actual data points that you have you added to training data? Does it mean that?
For each batch with the probability of 0.1, you either augment that data point or you don't.
And these augmented data points are in additional to training data. So you use all of the training data plus some augmented data coming from this probability.
So you have a fixed training set, okay? And for each batch, you get a batch of training data. And before you apply your update or calculate your update, you sample from this probability distribution that you have, for example, in uniform here with probability 0.1. And for each of these samples with probability 0.1, those samples are being augmented. There is, so the definition, the classic definition that we have, that you have a training data and you have an augmented data, is not constructed this way. For each batch, you can apply a probability, you can apply an augmentation with a fixed probability. And
so
that's what we are
losing
showing
some
here.
data points?
No, nothing is lost here, because we train for 100 epochs. So in each epoch, this probability is applied.
Okay, so because there are many epochs, it means that it sees all of the training data, and also plus it sees 10% of that training data as some manipulated augmented data points.
Exactly. But when you apply, for example, with 100%, it means it never saw the original training data. It always saw some part of the augmented data.
Right. Okay.
And for example, it makes sense for GANs. If you look, the errors for GANs is very high when we have augmented probability of 100%. It means the model was only trained on GAN-generated samples, and it never saw any training data.
Okay.
All right. Okay, so these are the results of stress analysis. If you remember, for each data point, we were estimating a probability that how likely is it that the prediction of the model changes if we sample from a neighborhood around an example, for example, a training example for a certain amount of number of samples, several thousand, what is the probability that this decision changes? So the higher this number it is, the higher the stress is. And we show the results for different augmentation probabilities, 0.1, 0.5, and 0.9. And we show this around the original or non-augmented training data around. So this X can be non-augmented or augmented or unseen test. These two, non-augmented and augmented from training, and this is from the test set. And we can, in here, we can see that when the augmentation is 0.1, we see a high stress around the training data for around the augmented training data for classic, while we see the highest stress around the test data for mix-up. And as we increase this probability from 0.1 to 0.5 and 0.9, we see the stress around the mix-up for unseen test examples actually increases, which means that as we apply more and more mix-up augmentation, the predictions of the models in the neighborhood of unseen test example actually changes a lot more compared to other augmentations. And this is actually another evidence, as we saw in the previous experiments, that the mix-up models were less adversarially robust. We can also see that the mix-up models have higher stress around the unseen test examples. And we also show with different epsilons, which means the radius was smaller or larger, and we see this actually consistently is the case. Although, for example, epsilon 2 or even epsilon 1 are quite large numbers, considering we are attacking with much smaller epsilons. So any question regarding these results? It might be easier if we discuss it after each slide, because there's a lot of results in here.
Sorry, I think I'm jumping in again.
Sure.
So why the CLS is so high? So when it is high, it means that it's more smooth, right? Or
When
other way
it is
around?
high, it means that the other way around. So around the augmented data, we see that the classic is actually higher. But around the unseen test data, we see that actually it's lower. So what it means is that you are comparing the distribution of augmented data to whatever that the model was trained on. So the distribution around that, the predictions around that might flip more compared to, for example, mixed up or GAN, because if the model, for example, if the generative model was overfitted, maybe the distribution of a generative model is much more similar to the training data, whereas in the augmented, it's not the case. And we can also observe that as we increase the amount of augmentation, the stress around the augmented data decreases. So if we only apply 0.1 with probability 0.1, we see that the prediction of the model around the augmented data might change drastically because the model has not seen enough augmented data. But as we increase the amount of augmentation, we see that this number actually goes down. But around the training data is not that important, because what we are interested in is the stress around the unseen test, which is the case in here, because a model could just overfit and learn all of the augmented samples around the training data, but still is not useful for us when we present our model with unseen examples. So these are the models that the...
Why mix-up is so different than the others? Untested.
So what we are showing in here is actually what we have, or actually is related to what we have shown in here. The models that are trained with mix-up are the least robust. So they are easily broken with any weak adversarial attack, which means that, for example, if we are, I have to go back to this slide. if we are training our model with mix-up, we are likely getting a boundary that looks like boundary 2. So it's very easy to flip the example. And we see this in both adversarial attacks and our stress analysis. In our stress analysis, we show that the stress is very high, meaning the predictions can be easily flipped. And in the adversarial attacks, we also show that these models break much more easily compared to the other models.
So sorry, you may already explain that the mix-up was basically a combination of classic and GAN, right? Or
no. So let me go back to the slide that I had for mix-up. So this is what we do in mix-up. We have one sample with a label and another sample with another label. For example, we have a cat with a label cat, and we have an image of a dog with the label dog. And we sample from some distribution, beta distribution or some uniform distribution, a value, for example, 0.8, and then we linearly combine with the weights of 0.8 and 0.2, the data and their one-hot vectors, and then come up with a new data and a new label. So the label for, if you see, I don't know how much is visible, this is an image that is a combination of 0.8 of the cat and 0.2 of a dog. So this is mixing these two images. And its label will be in the first dimension 0.8 and in the second dimension 0.2. That will be its label. It's like a smooth label, but with these probabilities. That's what mix-up is doing.
Good, thanks. Okay.
It might make sense for specific data spaces, but not for any data spaces, I would say, because, yeah, as we show for images, it actually doesn't make a lot of sense. Oh, perfect. Jan already shared the paper, I think. If you look at the chat, Navid, you will see the paper.
Yeah, thanks, Jan and
I still have a stupid question to ask, if it's okay.
Sure, go ahead.
We say that data that very high dimensional tend to be linearly separated. So what's the dimension of your data in that those tests they're pretty high dimensional from the CFAR, right?
Yeah.
So doesn't kind of your model with the ball kind of actually, won't you have like smoother functions anyhow?
Can you repeat your question? So I understand that we are talking about a high dimensional space, which is true. And your question is?
My question is the method you use for with the ball and the epsilon distance. Won't you kind of have like won't your data be smooth separated in that case of this data set, like in any case? So you won't have like something that's super complex function over fitting your data or something.
So your question is that if we have a complex data space, such as images,
is that model with the ball a bit redundant?
You mean the sampling will be redundant if the data was complex? It's actually the other way around. The other way around. So the thing is, when we have actually our model makes sense even more for high dimensional space, because as the dimensionality goes high, the mass is more on the surface in the high dimensional space. And that's what we are doing. We are sampling from the surface.
Okay.
So when you have a very high dimensional space, the mass of the data is more around the surface compared to, for example, in the center. There are more points on the surface compared to on the center. And as the dimensionality increases, this fact actually gets more and more valid at this point.
That means that your augmented data tend to be more ambiguous, like kind of be in the middle.
This just shows that we are covering more uniformly from the vicinity of the data point that we are interested in. It just means that, nothing specific. So we could go to a specific direction, or say, for example, we only take a step in the direction of a adversarial direction or whatever, or we could say we just sample uniformly. But we construct this epsilon ball because there is always more data point on the surface of this ball.
Okay, I think I can kind of get visualized. Thank you.
And
I
there
mean,
is
you have a
another
question in chat.
Can we think of 0.2 weighted dog as the perturbation? If so, can we say it might be due to that the epsilon used for evaluation is very different in terms of distribution from the dog image, so the mix-up does not help? So what we are saying is that the weighted dog is interesting. So you are saying that the weighted dog is a perturbation that we are adding to the distribution. So I think so the thing is, when we talk about adversarial perturbation, this perturbation is constructed given some adversarial direction. I don't think randomly weighting some training data has any specific relation to an adversarial direction, but it's a distribution. Whatever that distribution is for this given task, it's not helping. We cannot say more strongly why. We cannot say it's because linearly weighting an example gives an adversarial direction, because we cannot prove it. But we can only say that this specific inductive bias that is linearly combining from a high dimensional space is definitely not helping. But I guess you can think of it as a non-useful distribution, which is not helping the robustness of the model. I think you can say that. That's interesting, because what in the end we are interested in is what are, like, we have an augmentation, maybe somebody comes up with a new augmentation and we say, okay, let's augment your data with this. So what can we say with all of this? One way is to look at it as a distribution of augmented data and measure it somehow with respect to the distribution of the original data. But the fact is, and we have been looking into this, that if we use measures from the data space, it might not be that useful. For example, if you are looking into some, I don't know, Wasserstein distance of the augmented data to non-augmented data, it might not tell you much about adversarial robustness. But that's an interesting point of view, I think. Interesting question. So these are the results from the influence analysis. Okay. So we created these plots to show the distribution of influence values. Each point that you see on each of these plots represent a test example, and the x-axis shows the influence of a non-augmented training data, and in the y-axis shows the influence of the augmented data. And we are plotting this in a 2D space for all the test data, for all the training data that we have. And this shows, like, in overall, a distribution of influence of non-augmented versus the influence of augmented. So the first thing that we can observe very quickly is that the y-axis is much broader than the x-axis, and the data is actually spread this way. And this means that the influence from the non-augmented is much less compared to the influence of augmented. The influence of augmented data on the test set are much higher. This is the case for all different augmentations that we use with all different probability, and we also have the results for normal tested and adversarial tested. The first column is normal test, the second column is adversarial. The second row is adversarial, the first row is normal test. And it's the same for probability 0.1, probability 0.5, and probability 0.9. The second thing that we observe, maybe it's more better observable in probability 0.5, is that the mix-up has a different distribution than the others. And it seems that the actually influence that the model receives from mix-up on the negative part, for example, in this case or in the higher case, is much higher, which means that when we train our models on the mixed augmentation, the models receive negative influence from the augmented data. So these are the observations that we have, and we wanted to actually dig more to see why this is actually happening, why we see these huge differences between non-augmented and augmented. So having another look at the formulation of the influence functions, we noticed that this formulation uses the Hessian of the model, which is always the same when we are comparing the influence of the specific test example for augmented and non-augmented. And therefore, we started to actually, we calculated the gradient norm for the non-augmented and the augmented training data, and we plotted the histogram of the gradient norm of the models for different layers. And here is the distribution. And as we can see, the gradient norm of the augmented data is much higher than the gradient norm of the non-augmented data. So as I mentioned before, the Hessian is always the same when we are comparing the influence of a non-augmented with augmented, and the gradient of the test is also the same. So the measure, so the factor that is actually most influential is the gradient of the training data. And we can see here the gradient norm is actually different and much higher for the augmented training data. This indicates or hints to a point that maybe the difference with the influence values that we observed here is actually coming from the gradient of the training, augmented and non-augmented training. All right, any questions?
Does it tell us that the model learns to separate between real data and augmented data? So it kind of realizes which of them are augmented and which of them are real, and therefore gives the real ones higher gradients?
So what I would say about it is that because this model has been trained for like 100 epochs, and if the model sees a deterministic non-augmented training sample over and over, the model remembers that sample. So there is no high gradient. I mean, what I say, take with a pinch of salt, but my intuition is that when you apply stochasticity to a sample by augmenting it every time, it always looks different, and it might make the model to change more because the model thinks, oh, it's a new sample, I have to learn that. And every time it changes, and the model again tries to learn that example. Whereas if you have a deterministic model, deterministic sample, every time the model sees and it says, oh, okay, I know what to do with that model.
So you mean that since just trying to rephrase, so since the augmented data are just change a little far from the actual data, therefore the model doesn't see that as much new information, and therefore the gradient is low?
I think the gradient is low for the non-augmented. I mean, I cannot say with certainty this is what is happening, but what I think is that the non-augmented data is deterministic and the augmented data has some stochasticity, and learning a distribution, a data that changes all the time must be harder for the model. Therefore, the model is trying to update more, and therefore is having higher gradient norms.
But what would happen? What would happen then if you change all the experiment setup instead of like every time has a new augmented data, like create 10% augmented data and just have whole of that get trained a couple of times to know whether that comes from a stochasticity or that comes from model understand the difference of the augmented data and real data?
This is actually what we did, and we can confirm for a limited set of experiments that this is true. So we fixed our augmented data. Instead of changing for every epoch, we just created an equivalent amount of augmented data to the training data, and then we trained the model over and over on, let's say, if you have 100 training, you have 100 training and 100 augmented training, and we train the model, and then the difference actually shrunk. So you don't see this high gradient norm and high influence anymore. So this is the next step that we are conducting, because we will have to have another talk discussing those results.
Yeah. Okay.
But very, very interesting question, actually.
I mean, the question is that how much of that comes from stochasticity and how much of that comes from the fact that model knows that there is no much new information in these data points.
So that's actually, if I want to summarize my talk in one sentence or two, that would be the takeaway, that when we talk about augmentation, there are two different things, stochasticity and inductive bias. And when we talk about augmentation, we usually don't separate these two, but actually these two are different things. And each might have a different effect on the models. So that's what we are trying to do, to separate the stochasticity from inductive bias and look into them differently. Very good question. All right, so I think we are over 1 hour already. I quickly summarize the talk. So we talked about this framework that we provided to evaluating models, and we applied it for some classification tasks, and we analyzed the classification risk as well as the risk under attack for different data augmentations. We also provided some theoretical definition that allows us to define different data augmentations under one theoretical definition. And we showed that in the experiments we conducted, the expert-introduced data augmentations were the most robust and the most useful. And we also analyzed the decision boundaries of models using our prediction change stress, and we showed that the augmentations that were non-robust had a higher stress around the test examples, and we also used influence functions and showed that the models get more influence from the augmented data. So this was a group effort that has been done with my colleagues at the Institute of Computational Perception as well as SSCH. And we have two papers available online about the results presented in this paper. And if you're interested, you can look them up. And thank you all for your time. If you're interested, check out the link to the lectures, also for future talks. And if you want to learn more about the next steps of our research, check my website. And if you have questions, you can feel free to send me an email. Thank you.
Thank you, Hamid. Can you hear me? Okay.
Yes.
Thank you, Hamid, for your talk. It was very interesting. And even if we are over 1 hour, we maybe can accept some questions if you have any.
Thanks, Hamid, for that great talk. Actually, I want to ask you something to go back to one of my previous questions. Is you said that we can do that augmentation when the labels are not discrete. So can you
Okay.
Can you give me an intuition of how that goes? It has nothing to do, but
Are you talking about the regression?
yeah.
Okay. I mean, imagine you are doing some regression task on some natural images. You can just flip your image of a dog with, let's say you have some, I don't know, interest values for different breeds of dogs between 0 and 1, and you have a set of images of dogs. So if you have a specific breed, you can also flip it and it's still the same breed. So you can probably use it for the same. But it completely depends. So the takeaway of this talk is also that you have to look into the task that you're working on and think about what your augmentation is doing and think if it makes sense. So that if you don't flip it, if you flip your image and it suddenly changes the meaning of that image, then it might not be a good idea. But if you have something that doesn't affect a flip version, then it's probably fine. I mean, if you want more specific, maybe discussions about the specific task or project, we can maybe talk about it later.
Yeah, sure. Why not? I'm not in the level discussing more specifics, but yeah, just wanted an intuition about how it could be done with continuous labels.
So the data augmentation just extends your training data in any direction that you think might make sense. So you can use some data augmentation based on the knowledge that you have about the task, or you can just use some general purpose data augmentation, such as mix-up. What we show in this paper is that using general purpose augmentations might be dangerous because if you don't take the specification of your task and data into the account, you might end up finding a decision boundary that might look like it's having not a different accuracy, but it's a completely different model.
Okay.
So if you have a specific task, I would say you have to think about what it means and what your data space looks like, and then think about what kind of augmentation makes sense. So if you know the task and the data, it helps a lot to come up with new augmentation. For example, in audio tasks, it's very common to pitch shift a little bit or add some background noise to the data, which might make a lot of sense. If you are doing, for example, some acoustics in classification, that pitch might not change the meaning. But if you are, for example, doing, I don't know, pitch tracking, then augmented the data with increasing and decreasing pitch might not be the best. So you always have to think about.
I mean, if you can predict how the label changes, then you can still apply pitch shifting.
Yeah, that's true.
Also, I'm wondering if you inverse the phase on a signal, will that kind of change the result? It's just a.
I
would let my audio expert colleagues answer your question.
If you then compute the magnitude spectrogram, the magnitude spectrogram will still be exactly the same, so you won't notice.
Yeah, exactly. Yes.
But if you're training on raw audio, then it might help
you. Thank you, Hamid, for the talk, and thank you, Jan, for the answer.
Thank you all for your time.
Okay. Do we have one last urgent question? Okay.
It's not so urgent, but I can. Is there any way to learn this augmentation function?
There are actually very interesting papers came out lately that try to learn augmentations. Actually, I can maybe try to find them, but there are several that try to learn a transformation that is beneficial for the task. So it's actually a very interesting direction. I didn't look into them or evaluated those, but I have seen, and I think when you think about invariances that you want your model to have, it might make a lot of sense to just learn the transformation on the fly.
Thank you.
Okay. Thank you everyone again for joining this CP lecture. I just want to mention that probably the next CP lecture will be held in January directly, hopefully with a better situation about the coronavirus. One thing is that we will announce always the CP lectures on the Twitter account of the Institute of Computational Perception, which is pretty easy to remember, but I'm just going to put it in the chat now. And of course, let's say there will be the announcement, and you can always send a request through the Google form to join. For people inside the group, I just want to say that I will create a new channel on Mattermost where all of these will be managed, except including the recordings, including the meetings and the announcement, where everything can have one place there. And probably there will be some changing of the CP of the structure of CP lectures in order to make it more publicly available to the others. Okay, and said with this said, I wish you to have a nice meal, and see you next time. Bye.
Bye.